Morning, guys. So today we'll discuss about the reconfigurable antennas, what are reconfigurable antennas, where do we use them, and I've selected a reconfigurable antenna paper, and we'll discuss about the reconfigurable antenna paper, and then we will directly go to the HFSS and design that paper. So the geometry and fundamentally what is a reconfigurable antenna, and why do we use reconfigurable antenna? See, every antenna has a spot on frequency. Okay, so if we wanted to change that spot frequency and without getting a new antenna, so what do we try to do? We change the geometry. Okay, so once we change the geometry or the passage of the EM wave towards other direction, because of the length or being changed, or because of the any physical parameter being changed, so the frequency is being changed. So you can see in this graph there are multiple spot frequencies, 1 2 3 4 5 6, around 6 spot frequencies. You can see this based on the voltage level inputs, the frequency has been changed. So without dynamically whether there is an input from outside towards the antenna, the switching mechanism gets on and off. As simple as that. So there are three parameters in the antenna which we try to do the reconfigurability. One is the frequency reconfiguration, and the pattern and the uh, polarization. Okay, so these three are there, and frequency reconfigurability, pattern reconfigurability, and polarization reconfigurability. So these three we'll try to figure out and see where we can do our best. So this is a theory of background theory for the reconfigurable antenna. So we'll directly jump into the uh, a IEEE paper. So a paper I've looked at. So actually, I thought explaining the reconfigurability concept with this kind of structure would be easier rather than going for a complex structure. So I was searching for a monopole slotted antennas. So since then I couldn't get that monopole one. So now, in this case, we'll try to see. So I'll explain you simple. So there are multiple patches here. I mean, 3 into 3 array matrix patches. So 1, 2, 3, 4, 5, 6. So this is the one. One. So I'll try to take it. So, so this is 1, this is 2, and this is 9. So you can see 3 into 3. And what they're trying to do is they're trying to connect with these the cover patches. So here it is the copper patch in the design, but generally they'll try to go for the pin diode or RF MEM. So they'll keep a actuator or a sensor kind of a device between this pixel patches. So well, let's suppose 1 and 2, and they'll try to create this C1, let's say 1 and 4. They'll try to create the C1, and whenever they required a configuration for which a frequency they want, they'll see the optimization iterations. For example, if you have this kind of design, you are getting a frequency over in this band. Okay, when you are going for this kind of a design, you are getting a frequency in different frequency. So based on the frequency, we will try to do. So as you can see the connection tabs, okay, based on the connection, the frequency has been changed. Based on the frequency, the return loss gain and this. So one antenna can give multiple frequencies and multiple gain and so polarization. So these are there. So that is a basic concept of reconfigurability. So now I just don't want to get into the theoretical part. How do you design this all things? Okay, that would make too lengthy. So I think this paper I have gone through, so it is quite good enough to understand like how can you start for the theoretical concepts. Okay, so fundamentally, if I'll start designing the geometry of the structure, 3 into 3 array matrix in the HFSS software, and we can see from there. Okay, chalo. Let's go start from HFSS. Now, once if we see the geometry of this, so the basic thing we need to figure it out is the length and width of this pixel and this connecting copper patch. Okay, anyhow, this is a square matrix. So all the lengths are equal and all the connecting copper patches are equal. So I've calculated the length and width of the anyhow the length and width is there. So length and width is 7.3 and 6.5 mm. And for this one, so I have calculated with this PL and PW. So when we calculate it came around 2.5 into 2.5 mm. So that is there. So now we'll try to design this 3 into 3 matrix first from HFSS and then we will design the entire substrate structure. Okay. So let's start. First, take the insert. Okay. New project. So I've inserted a new project. So I'll directly start jumping off. So I'll try to make it off. So the main fundamental thing is, so I like to start in this way. So from here to here, from here to here, from here to here. So what is the outer dimension for this substrate? That's one big question. So I'll just have an assuming like this now. So I'll see if the total length of this is 26.9. So definitely this and this when it's joined, it's 26.9. So I'll take twice of this PW and twice of this PL. So that's how I'll try to take, and that would be good enough. From there, so I have to calculate this one also, this position. So how much will it take? So instead of that, I'll try to calculate from here to here and from here to here. So that would make it easy. So because we know center, from center to here, I think it would be half of this and then the length of this and then the length of this. So that becomes this position and from here to here, the same distance we have to minus to the left side. We'll get that distance. Okay. So basically, if you are not able to get the values in your paper, so just apply basic algebra and logic. Like how can you get those values with the available values, whatever you have. Okay, so that's the basic thing. So everyone has different ways to figure out the values. So I'll try to go for the simpler one. Chalo. Uh, I'll find out the values of I'll find out this position and start the design. So I've calculated the position for this one. So I'll try to write it in with different color. So from here to here, so the length is around 12.25 mm and so I can make it that I can take a center from a line and just draw 12.25 mm in this direction. From here, again from this center to this one, it is around 13.45 mm. So 13.45 mm. So this is one more direction. So we can start the design from here. So from this position, we can just copy paste everything and just create it. Okay. So I'll directly go to the HFSS software. So now I've created a substrate. So that's a box. And now once we go into the box and give the variables. So length of substrate, LOS. I'll put it as LOS length of substrate. So that is so in which direction it is in X direction. That means it's a width. So that is PW into 2. PW. So there's no going to be PW. So I'll just write 26.9 into 2. Okay. So mm. So that is 53.8. So again I have to write Y. So that is PL So the L line of substrate, length of substrate. Okay, this is width of substrate actually, not the line. So we have to change that again. So there's little bit confusion. So first this excess width. So I'll just write W1. That would be good enough. W1 is equals to um, so PW into 2. So, so what is PW it asks? So I'll just write 26.9 mm. Okay. And Y size, that is L1. So that is PL into 2. So I can write PL as 24.5. So that is 1.6 H. So that is 1.6 mm. Okay. So that's FR for material. So now we have this. So I'll just put Control D. So now we got this. So the first thing is have to take a, what do you say, line. So edit. So now, so I've clicked on the center 26.4. Now I need, actually the basic thing which I try to do is y distance set. Okay. So I want to change only one direction towards down. So that's why I'll try to change only one direction. So 26.4, 26.4. So I'll just try to minus mm. I have to write here mm. So how much would be good? That would be go for down. That is 12.25 mm. So 12.25 mm, and that's there. I think it went down. So now from here again, we need to take a uh, draw a line. So from here, why I'm trying to zoom is that there shouldn't be change in other directions like an X and sorry, in for this case there should be no change in Y and Z. So that's why I'll try to zoom it and give it a small one in the starting, and then I'll put exact value. So that is 13.45 mm. 13.45 mm. So that is there. Now I apply, and so now we got the starting position point. So first we can take a rectangle. So draw a rectangle. So, so, so I'll just try to name this as patch 1, P1. Okay. I'll just type it as L. So x-axis is not L. So I'll type it as W. So W is what is the W? 7.3 mm. 7.3 mm. And L is, how much is the L? That is 6.5 mm. Okay. So now we have this. Okay. Now again, the problem is I have to create this other rectangle from there. So again, I have to take care. So I try to So I'll try to see. So x is the length and width is the height. So first I'll try to give the x. That means the width. That is, I'll write CW because the patch, the coupled patch, CPW, coupled patch width. So that is 2.5 mm, and I'll just give minus CPL by 2. CPL by 2. So I'll not give minus here. I'll just give CPL by 2, and I'll give CPL as minus, what is it? 2.5. 2.5. Yeah. So that is minus 1.25. Now if you apply, you have this graph. So now what I'm trying to do is, so I'll just copy this and paste it again. And I'm gonna move this one, operations, and move from here to here. So this becomes the single. Uh, so now you can see, so I'll try to measure it. So this is should be 2.5 and this is 2.5. So now the only thing that left is just copy paste. Okay. So why there is a um, move? That's okay. Nothing changed. 0.6 correct. 6. Okay. So I have to do the copy paste operation currently now. I'll just show it for only one patch. How can you do it? And you can go for the rest of the all the patches. So first we have to select the P1 patch and then the copied one. So I'll rename this also so that next P1. Okay. I'm not mentioning exactly as the paper like this. Okay. P2 and first we have to move this one, right? It's it arrange move. Okay. Now the CP2 has moved. Okay. And let's C2 again. Edit, arrange, move. So this is also moved. Okay. Now FTC P3. Okay. Now you have this P3 here. Click on the edit option, range, move, take this and try to make it a center one. Okay. Now you can select all these. Select only C1 and edit. First you have to first just copy this one, paste. Okay, three times I've tried to paste it. So C3, C4, and C5. Okay, first I'll try to take it C3, edit, arrange, move. So my advantage is because it has been, what do you say, the square. So that's why it is not more too difficult for me. Yeah, arrange, move again. Edit, arrange, move. Okay, so this is an it has been done. So now I have to move all these patches P1, P2, P3. So I'll just try to move all those one. So I'll try to move all those pins once, arrange, move, take this, just that's it. Okay, and now just P4. Now you can select this and this one C3, C4, C5, and you can select again P4, P5, P6. Copy and paste and click on this right, edit, arrange, move, click on here, that's it. Okay, now you have the square option. Now the only thing which is left for you for the right angles one, I mean the in the X direction you have to make it that these two should come in this four positions. So let's see what are this. So C5, C6, C2, C3, C4, C7, C1, C2. Okay, C1 and C2 are there. Okay, edit, arrange, move, and C1 and C2. Again, copy, try to move it, edit, arrange, move. So I choose this design because of this simpler design. Like I choose this paper to explain it in very simpler concept. So that is what the main thing. So I'll try to give all the patches one color and all the patches one color. How can I assign color? Edit properties we have to go. Okay. So I'll get to give them the orange one. I like to give the bright colors on the top and this all the C1, C2, C3, C4, C5, C6, C7, C9, C10, C11, C12. I'll try to give this a different color. So um, gray would be fine enough. Okay. So gray we can give green also. So gray I'll give gray. So because substrate is always green. So I'll try to give the substrate as dark green. Anyhow, it's green color. So I'll give the dark green color. That would be good for me as well. Okay. So that would make it simpler. So now we have this. Okay. So there are two types of feeding. So one is the wave type for feeding, and other is the lump feeding. So in this paper, they have shown the wave type port feeding. So we'll do that. It's not too hard. Just you need to understand what are the widths and inner core widths and outer core widths of the SMA connector or the port, whatever you're trying to give. And if you have the good idea on the position, that is fine enough. Okay. And chalo, now I have to save this. And so first I'll try to give the perfectly basic conditions I'll try to do and change the configurations in different workspaces and simulate it and see. Okay, so first the condition is to give the perfectly conditions for all these. So whenever I try to after designing, so my way of designing once it is like once you finish all the geometry design, go from the starting. If you have to see each and every material, whether what are the things if you wanted to do for each and every material, those things you need to apply and go for same as a synchronous way. So that would be good enough because of the vacuum box it's there, vacuum is there. That means I have to change it into the material. So I go for the edit and that's FR4, right? FR4 So it came FR4. So I'll click on the FR4, apply, and then go OK. So now here we came for the perfectly conditions. I'll just okay. I have to select all these points now. So assign boundary condition perfectly. Okay. Now that's perfectly in all the cases. So now I have to create the ground layer. Let's go to the bottom. That's it. Draw a rectangle. So I have to name this as ground, and I haven't always I go for ground as pink because it look good when you see. Okay, so that is there. So now ground is also a perfect T. Okay, now it has been done. So the only thing which is remaining in this kind of excited like this one is the excitation. So that I will do. So just a minute. I have to save this one. So my name is Nagraj, by the way. If you wanted to see many more videos on HFSS or ADS designs, you can check in my YouTube channel, or if you have any technical questions, you can get into my LinkedIn. I'll drop it in the description, and you can ask me over there. If I have the knowledge to answer your question, I'll definitely reply back. Okay, so I'll save this as reconfigurability. Reconfigurability. So in the last thing I stopped where how did the SMA connection could be done. So instead of that SMA connection, I've tried to create this rectangle, and I gave the 2 mm width of this rectangle and gave the lump port excitation rather than the wave port excitation. So I wanted to see where did I do mistake. So in the next video, I'll definitely put on the concept of how we can do the wave port excitation. I think I did not give the perfect key, so I have to see where exactly did I do wrong. So, but for this one, I've done the Lamport excitation. I think you know how Lamport excitation can be done. So if not, you can watch it. Once it is there, now you can go on to the results, right click, and you have plot, and you have one frequency. It is not much good. So at 2.5 gigahertz, you're able to get that frequency. And so now we will see the cases and try to see. So this is one case where we got here return loss minus 14 dB. We could get minus 5 dB. We got. So this is 3.9. That means C4, C3, C4, C5, and 3.9. So these are the two conditions. Okay, only these two are gone. Rest of the all are there, if you can see. So in this case, all these states are gone. For this one at 10 gigahertz at 3.9, I think. Let's say for the first condition, we'll try to go for this one because we have done this one. So this in this case we got 2.6. So next we'll go for this condition. So only the upper two patches are gone. So I'll just copy this, paste here, all case 2. So I'll try to. That's why I didn't. What do you say? United these all things. So if I the upper two post parts. So this is there. This is. So this so this is gone, and this is gone, and what all are gone. So this is also gone. The first three gone. So what is this one? C7. C7 is gone. So it is like this. Have to see. So it is like that. Chalo. So now that's it. Rest of everything is same. Save, validate, and let's remove this one. And we have to change the frequency setup also. Uh, Now, what is the frequency we are trying to do? So, 3.9 gigahertz. Let's take, so let's remove this one and add a frequency solution setup at 3.9 gigahertz. So, so that would be fine enough. I'll try to convert this. So I'm not doing that discrete level simulation. I'm just trying to do the interpolating. Okay. So the simulation has been started. So in this case, we'll see the gain plot. Okay. And the last case we couldn't see. Gain was around 4.35. So let's see whether we can see the gain in this case or not. Results, far field reports, 3D rectangular plot, gain, dB. So there's no gain in this. This is okay. Far field, first field reports, radiation pattern. We can see from this also. I have to see. Okay, for this, I have to click on this minus 180. And okay, but still we have to add marker. Let's see. We got around 1.5. 1.5 at 0 degrees. Okay, chalo. I think the progress has been done. Okay, we'll go to the case 3 and see. Okay, case 2. I think this is done. Go to the results. S11 plot. Okay, we got a frequency around 3.7 up 7 dB. Okay, again one more 6. Okay, so around minus 7 dB we got it. So it's around, it's 19 dB. Okay, there's a huge difference. Okay, and so there's around 10 gigahertz. So this is the concept which we try to do. So if we plot in the overall spectrum, they will get multiple frequency plots. So now, okay, I'll try to see the gain plot for radiation pattern, dB gain. Okay, 2.79, that means 2.8. So it's 3.52. Let's change. Okay. So 3.56 he got when it was measured, and 3.7. So there's a little difference, but I think you have an idea how the reconfigurability works and like what do you mean by it. So in this video, I couldn't explain about the SMA type waveport excitation. But in the next video, definitely I'll explain. And this is the concept for the reconfigurability, frequency, and pattern reconfigurability. Okay. So next video, I'll try to design another uh, concept of antenna. That's it for today. Thank you. Thank you for watching.